Good morning, dear student. Today we have to study about the elastic potential energy of a spring. The spring is always having a spring constant and which is following Hooke's law. So according to the Hooke's law, F is directly proportional to the negative of displacement. It means the restoring force is always equal to minus k into x. In this case, see what is happening on this spring. The mass is connected on with this spring, a rigid surface is connected. It means on this spring there are two objects which are applying force. One is mass, another is rigid surface. So see, this is the equilibrium position and we say there is a neutral position. So in this case, neither this mass is stretching it nor this rigid surface is pulling the spring towards itself. So that's why we say this is the mass of a spring is taken as how much? 0. So in this case, according to the Hooke's law, F is directly proportional to minus x. Replacing proportionality sign, it comes k, so it becomes F is equal to minus k into x. So this is called Hooke's law, or force applied by a spring on the mass. Now suppose this mass m is kept on an horizontal frictionless surface. The spring is having its mass how much? 0. And now I had stretched the spring by how much distance? X distance, or I had compressed is by how much? X distance from its mean position or initial position. Either I had compressed it or I had expanded it by how much distance? X distance. So what is happening? Either compression or expansion. So what will happen in this case? Its energy will get changed. So see, at this initial position energy was 0. As I will compress it, so I will do certain work in compression. So work energy theorem says the change in total mechanical energy is always equal to work done. So what is total mechanical energy? Change in internal energy plus change in kinetic energy. This internal energy is exactly static energy or potential energy. So change, always I had to find out initial minus final. Why? Because work energy theorem says whatever amount of work we are doing on an object, so that work will be utilized in increasing the energy of the object. If a system is doing work, so that work done will be always equal to work done by the system. So in this case we are doing work, so energy of the system will increase. So that's why increase in energy I have to find out Vi minus Vf. So this will be the increase. So this will be minus, and this is dw. dw is equal to f into dx. F is equal to minus k into x. So it had become minus, and minus will get eliminated here. So what is left? Ux, that is called final energy at x distance, is equal to k is constant integration of x with respect to dx. On integrating this x with respect to dx from 0 to x, so it will become half kx square. So what is this? This is called elastic potential energy of the spring. Now in further continuation, suppose this massless spring is not on the horizontal surface, it is in a vertical plane. So what is the difference between horizontal and vertical plane? In horizontal plane there is no role of acceleration due to gravity, but in vertical plane there will be definitely role of acceleration due to gravity, small g. So in this case, how energy is getting converted, this I am going to explain for the spring. So vertical spring, elastic potential energy and gravitational potential energy. So in this case it will have how many energy? That is 2 energy, elastic potential energy and gravitational potential energy. So this is the initial position, we will say neutral position. Initial position, the mass which was massless, the spring which was massless, no mass is connected. But suppose I had connected a mass m with this spring, so what will happen? Length of the length of the spring will increase. So what is the increase in length now? X. So after that it will be again in equilibrium position. So this position is equilibrium. So how equilibrium? Because at this position two forces are working on a spring. So mass is applying force downward and spring is pulling the mass upward with restoring force k into x. So but at equilibrium both should be remain equal. So as you know, that is at point 1 the force of a spring the force of a spring is how much? 0 in this case. Why? Because mass is 0. But in figure number 2, which is in equilibrium, force by the rigid wall, this wall is 0. Why? Because mass of the spring is again how much? 0. But on a spring, how many forces are there? There are 2 forces. So on a spring, force by block. So a spring is applying this how much? M into G. Block is applying force on the spring, M into G. But the block force on the spring, so spring by block, the force on the spring. So that is K into X. Exactly, you have to understand this. Spring is applying force on mass upward and mass is applying force on a spring downward. Understood? M into G. But this position is in equilibrium, so M into G must be equal to K into X. So M into G is equal to K into X at equilibrium. So X is equal to mg upon K. Is this clear? If it is so can I find out elastic potential energy? You know, formula of elastic potential energy is half kx square. So substituting the value of x here, that is mg upon k. So it is half mg square upon k. Half m square g square upon k is called elastic potential energy of the spring. It is depending on spring constant as well as small g, that is acceleration due to gravity. But this is the second condition here. So in this third condition, now what I had did, I just stretched this mass by how much height? H height. So what had been changed? Its potential energy also has changed. So elastic energy as well as potential energy has been changed. So see, just after stretching, the total energy is equal to, just after stretching, so total energy is kinetic energy because I am stretching it. So I am applying the velocity, I am giving a certain velocity, so velocity, kinetic energy plus potential energy. Potential energy is equal to half m square g square upon k. This is the potential energy. This was the total energy. But for h displacement, now how much displacement? H displacement at this position, it means it is having elastic potential energy half k into x square. So what is x is equal to for this position? This is x plus h whole square. And what is the value of x? You know, x is equal to mg upon k. This already you know. X is equal to mg upon k. So this is the value of x is equal to mg upon k plus h whole square. This is elastic potential energy. But at the same time, on a stretching, there is what? Change in gravitational potential energy, h of the displacement. That is how much? Minus m into g into h. Why it is minus? Because the body is coming downward towards the direction of acceleration due to gravity. So this is minus m into g into h, decrease. So at h displacement, energy at h displacement will be how much? Kinetic energy 0, because there will be no velocity. So what is the total mechanical energy at point h? That is half, that is potential energy, elastic potential energy and gravitational potential energy. No kinetic energy is there. So total energy was this much. But according to the conservation of energy, both energy at equilibrium as well as energy at this point, that should remain constant if no external work is done. So both must remain equal. So now this is the energy at point at equilibrium, and this is energy at height h. Equating them together, so you can find out what is the relationship of velocity. So v is equal to h under root k upon m, or h is equal to v under root k upon m. So this is so simple. So you have to find out what? Velocity or height, displacement from the mean position. So mechanical power, you have to study. This is so simple. That is work done per unit time is called mechanical power. Its unit is joule per second, or this is also called watt. And you know, 746 watt is equal to 1 horsepower. This is 1 horsepower. And W is equal to P into T, that is watt second is the another unit of work. So that's all for today. Go through the content and check out your work. So that's all for today. Thank you and have a great time.